Ja, danke. Und ich spreche ein bisschen Deutsch. Ich glaube, ich bin der deutsche Teil hier heute in dem Blog, aber wir sind ja die deutschen Auslandsschulen. Und ich freue mich heute ganz besonders auf Professor Stefanie Müeller aus ganz vielen Gründen. Erstens bin ich auch aus Sachsen-Anhalt, wo sie angefangen hat zu studieren. Und dann habe ich auch lange in Berlin gewohnt, wo das HPI ist. Und ich glaube, Professor Müller ist unsere jüngste Sprecherin in der bisherigen Lecture Series. Und da ich ja auch Mathe und Physik irgendwann mal studiert habe, interessiert mich das Thema ganz wahnsinnig. Aber ich finde es auch für euch Schülerinnen wahnsinnig interessant, heute einmal zuzuhören und auch so biografisch ein bisschen interessiert zu sein. Hier haben wir mal einen Weg von einer kleineren Universität in Deutschland direkt als Juniorprofessorin ans MIT. Und da wir gestern unsere Kanzlerin hier hatten in der Schule, ist es sicher auch was gestern eine Rolle gespielt hat, zu sagen, findet raus, was euch interessiert und once you're dedicated, it works out. Und das ist, glaube ich, eine ganz wichtige Message heute. Und was ich auch nochmal sagen möchte und auch den New Yorkern, die heute zugeschaltet sind, gerne anbieten will, wie bei uns in der Schule, wer regelmäßig an der Lecture Series teilnimmt, kriegt mit dem Zeugnis auch ein Zertifikat, dass ihr in der Schule schon an Vorlesungen teilgenommen habt und die Vorlesungsthemen, und das ist sicher auch was man in seine Bewerbung gut einbringen kann. Es hat also auch diesen Nebeneffekt, und ich übergebe jetzt gleich an John Halpern vom HPI New York als die bewährte Organisatorin unserer Lecture Series. Also wirklich eine ganz wunderbare Zusammenarbeit, und Miss Halpern wird auch wieder in unser BESO-Programm kommen, also auch mit euch nochmal besprechen, welche Erfahrungen sie hat mit Studiengängen, die in Deutschland und den USA angesiedelt sind, wie man hin und her gehen kann und wie man den richtigen Weg für sich findet, wenn man nur weiß, was einen so wirklich richtig interessiert und wofür man brennt. Ich glaube, das ist so das Wichtige, und das werden wir jetzt gleich merken, wie alle hier für diese Lecture Series brennen und auch für das Thema, um das es heute geht. Und ich übergebe jetzt an Joanne, die uns Professor Müller vorstellen wird.
Thank you so much, Katrin, and also to the entire GISSV team, Thomas, Michael, Heike, all of you who've been involved in organizing today's event, and especially our speakers. It's a privilege for me to introduce today's speaker. Professor Stefanie Müeller is an alumna of the Hasso-Plattner Institute, where she completed her PhD. She's currently an associate professor in the MIT Electrical Engineering and Computer Science Department, jointly with MIT's Mechanical Engineering Department. And Professor Mueller is also head of the Human Computer Interaction Engineering Group at MIT's Computer Science and Artificial Intelligence Laboratory. For her research, she has received a National Science Foundation Career Award, an Alfred Sloan Fellowship, a Microsoft Research Faculty Fellowship, and was named a Forbes 30 Under 30 in Science. Her work has been awarded several Best Paper and Honorable Mention Awards at the ACM-CHI and ACM-UIST conferences, the premier venues in human-computer interaction. Professor Mueller's work has been covered in top news outlets such as New Scientist, BBC, and Fast Company. She's also served in many leadership roles in the human-computer interaction community. And I also wanted to just welcome Eberhard Högeler, who worked with me at the Hochschule Harz, where Stefanie did her bachelor's in Wernigerode. He came today, so Eberhard, welcome also. Stefanie, it's truly a pleasure to have you here with us today, and we're looking forward to your presentation. The floor is yours.
Okay, thank you so much for the introduction. It's so nice to be here today, and just to emphasize, I had actually a cold over the weekend. So yesterday I canceled all my meetings and I had a silent day just to save my voice so I can give the talk today. It's also actually my first time being at least virtually in American high school, because as Joanne already said, I actually went to high school in Germany. So it's so nice to see you all remotely at least. I also know it's super early for you, so I totally understand, if you're still a bit sleepy, but I hope I can show you some interesting projects today. So yeah, just about myself, super briefly, Joanne already said it, I'm from Germany, so you can also ask me in German anytime you want. I'm from a teeny tiny town in Germany. It's called Schkopau. There's only about 5,000 people live there. So it was really not obvious for me that I at some point would end up over here in Boston. Also, there's nobody in my family who did a PhD research program, and there's also nobody in my family who became a faculty member. There's also nobody in my family who lives abroad, so it was really kind of a crazy path to get here. So if you have any questions about how I ended up here, I'm super happy to answer them, after I showed you a bit about my research. So yeah, the path doesn't always have to be straight, as you already said. Okay, so what's my research? So in my research, I look at what computing has changed in the past and what this means for today. So I would just give you like a quick example of this, right? So in digital, we can do amazing things these days, right? So let's say you have a 3D editor and you just want to change the appearance of this car here. You can just click a single button and you could like recolor the car here, right? Or if you have a photo, you can like simply load it into like your Instagram profile. You click a few buttons, you can recolor your photo and make it look like super pretty, right? But in physical, those things are unfortunately not that easy today, right? So I think most of you are probably too young to have a car. I think a few of you may be at the right age. If you wanted to recolor your car on a daily basis, right, that wouldn't be so easy. You would have to bring it to like a car maintenance shop. And it will cost a lot of money, so probably not many of you could actually afford it, right? It would just be like too expensive and too time consuming. So one of the questions I have is, can we somehow bring these capabilities that we have for digital worlds to the physical world? So for instance, that we could actually change the car's appearance on a daily or even an hourly basis. So what if we can give these like physical objects digital capabilities? And I will spend the next like about 30 minutes to show you a bunch of different examples of how this could work and what we can do with this. So the first one is reprogrammable appearances. And I will show you the first project here. So we developed a smart material that you can actually spray onto objects, and then by shining some light on them with a projector, you can recolor their appearance. So here, this is a classical example of a chameleon being recolored. Our material is fully erasable, so you can always erase it and then recolor again. This is maybe a bit closer to what you would perhaps like to have. This is a phone case you can recolor on a daily basis or hourly basis, a pair of shoes. And then, I love cars, so we also made a miniature car example. It's not full scale, it's like a little model car, but I hope it gets the vision across. So yeah, as you can see in the corner, like our method still takes about like 40 minutes per site you want to recolor. But so it's not quite at the digital capabilities yet where you just click a single button, but it's definitely much faster than if you would have to like repaint the whole surface and then somebody would have to carefully like engrave the patterns into the car. So yeah, I want to show you these images one more time. So this is the phone case that we recolored. So again, you just take our smart material, you airbrush it on with a little airbrush, you put it in front of a projector, and we can reprogram this material into any texture we like. This is the shoe. So just imagine maybe in the evening, you put your shoe in front of the projector, right? You recolor it, and then the next morning you walk out of a new pair of shoes. This is the car. Particularly, we were excited about like car sharing applications. So if you do car sharing and you get like a car from somebody else, right, it always has like the same appearance and you may not like this appearance. So could we increase car sharing participation by making it a bit more personalized? And then this is like a more futuristic example. We haven't built this yet, but imagine you would take our smart material and you paint it onto the wall of a room, or you paint it onto your furniture. And then maybe while you're still in school, you can open an app and you select like how you want your room to look like at home. And while you're going home, our smart material would reprogram itself and your entire room would look different depending on how you like it for the day. So this looks all cool, but you may be asking yourself like, okay, but how does it actually work? What's behind this? So yeah, how would this work? And obviously, these things are always pretty complicated. We spend a lot of time doing the research for this, but I hope I can break this down for you a little bit so that you can follow along. If you have done any optics work in your classes, that would come in handy here because it's all about what light can do to a smart material. So our smart material uses these materials. They are called photochromic dyes. And by default, they are transparent. So now if you shine some UV light on them, they become colored. And now you can use them in your normal environment. And if you shine some visible light on it, for instance, from like a normal office projector that I would normally project these slides on, you can actually turn them off again to become transparent. So the process is fully reversible. You have these materials, you shine the UV light, they become colored. You shine some visible light, they become decolored. And you know, these materials, you can actually just buy them, right? So we ordered them from a company in Japan, and then we just mix them into a liquid to generate these materials. So one problem with these materials is that they are typically only a single color. So you can buy them from the company in Japan, but you can only buy, let's say, cyan separately, you can buy magenta separately, and you can buy yellow separately. So while this is good, you know, you can paint the whole surface with cyan, then you can get a cyan image, but that wouldn't create these like multicolors that I showed you at the beginning. So here's how we create these multicolor textures. And this is now getting a bit more into the optics, and I hope you can follow me for like 1 or 2 minutes on this. So the idea here is, it's actually pretty simple. We take the cyan, the magenta, and the yellow that we bought from the company, and we just mix it together, right? And if you have done some, you know, art class or again, some optics in school, you know, that should make sense that if you mix those together, right, you get black in the end. So this is also very similar to how your inkjet printer works, right? If you still have a printer at home for printing out your paper sheets, right, that has a little ink containers inside, and they are like cyan, magenta, and yellow, and by any combination of these, you can make any color, including the black color. So how can we now we have all this material in a single bottle, right? How can we make all of these different colors? And the idea here is that we will try that within this bottle, we will make one of the colors transparent. So let's say if you have this black bottle and you make the cyan transparent through some magic way that I will tell you in a second, all you would have left visibly to the eye would be the magenta and the yellow. And these two colors together, as you can see, would create red. So you get the red bottle. So how would we, for instance, make the green color? Well, again, we take the black material in the bottle and we try through some magic way to make the magenta transparent. So all that would be visible to the eye is the cyan and the yellow, and you would get green. So this is like the high-level principle of how we can make all of these different colors by making a portion of each color in the bottle basically transparent. So how can we make them transparent? This is where the optics comes in. So this is the last complicated slides I will show you today. You see the wavelengths on the bottom. So these are the wavelengths of light. And then you see our 3 materials, the cyan material, the magenta material, and the yellow material, and their absorption spectra. So basically what this means is if we shine light of, let's say, this wavelength here, we would mostly make the cyan transparent, but the rest would still stay saturated and we would still see it. If we pick, let's say, light sources roughly here and there, we would mostly make the magenta transparent or the yellow transparent, depending on which light color, like which light wavelength we would shine onto the material. So how can we shine these different light sources? Well, I already said it a little bit. We are lucky that if you open up a normal projector like you would use for projecting slides, it already has 3 light sources. It has a red LED inside, it has a blue LED inside, and a green LED inside. And lucky enough, those exactly are in the positions on the light spectrum where we need them to deactivate the specific colors. So to show you this in practice, what this means is that basically we start from black and then we shine either red light, green light, or blue light from the projector onto each pixel to go from black to a specific target color. So this is how we can make these different multicolor textures. If you wanted to try this at home, again, all you would have to do is to buy these materials, you mix them all together. And you could, for instance, just make a red slide and just put the little bottle in front of a red projected slide, and you would already see some color change there. So this was a lot of like technical detail for the how does the optics works. I also want to show you the material mixing just to like take the scariness away a bit. So we literally just bought like automotive lacquer from a hardware store, and then we mix these photochromic dyes, which are just like pigments, into the lacquer. So we do this for the cyan, the magenta, and the yellow, and then you get 3 bottles of lacquer with the photochromic dyes. And then we simply mix them all together to create the black dye. And then you have your material ready, and you can just like, we mix it a bit together, and then you can just like airbrush it onto any object you like. So except for the more complicated optic part, this technology is actually very affordable and applicable, right? Because all you need is our smart material that you can easily mix together, and you need a projector to program the colors, and that's it. So I want to show you a few of the projects we are working on to follow up with this work. We also created a quick grayscale preview. So you saw the previous one took always like 20 to 30 minutes. This one here can now actually be done in roughly a minute. So we made some adjustment to the projection to create this in like, I think it's roughly 60 seconds to make this image here. So it's still not quite the speed of photography, but it's kind of getting there. Right? And then this is something I'm also really excited about, is to put this into textiles. So on the left side, you see our current system. We have this like big projector, and we have the UV light source that I talked about, and then the object is on the platform. But our goal is to actually get rid of all of these projectors and to put the light sources directly inside a fiber. So on the right side, you can see the latest in functional electronics for fibers. So you can now actually put like tiny, tiny LEDs inside fibers that can then be woven into clothing. So if we now use a red LED, a green LED, and a blue LED, and a UV LED, we have all the light sources already in a fiber. So we can just coat the fiber with our photochromic coating, and then we can literally just like turn on the fiber LEDs, program a specific color, and then turn them off, and we can have like reprogrammable clothing as well. All right, so I showed you one way how we can create programmable appearances. I want to show you two more. I will go less into technical details, but I thought I'd show you the videos as well. So I'm sure when you bought like birthday cards or any sort of, like celebration cards, maybe you have come across these lenticular lens cards. So depending on how you hold them, you see a different image from a different angle. And these cards work by having teeny tiny lenses on their surface. You can't really see them, they are so small, but there's small lenses all across those cards. And these lenses have different color patterns underneath them. So for instance, here, this is a simplified illustration. Let's say you have a red and a blue color dot underneath a single lens. If you look from the left side, because of how the lens magnifies the color pattern, you would only see the blue. But if you look from the right side, you would only see the red dot. So this is how these lens cards work. Depending on how you look, you see a different part underneath each of these lenses. So there's like thousands and thousands of lenses on these cards. So we thought, oh, this is kind of cool, but why does it only exist in 2D? Why is it only flat? And it turns out that actually just since like a few years ago, 3D printers are good enough to print not only full color resolution, but also print this optical clear material that's needed for making those lenses. So with my PhD students, I thought, oh, how about we just take this new 3D printing technology and we try to make these lenticular effects 3D. So here you can see this on a 3D printed object. This comes from this expensive Stratasys 3D printer that I just showed you. And you can see how the same effect works on this 3D printed airport case. So the whole thing here is 3D printed in one pass, which can also show you like how good 3D printers are these days. And to show you some more useful examples, not just decorative, we also made this kettlebell here. And if you train and you do your sports exercises, for instance, the kettlebell can show you, are you holding it too high, too low, or are you holding it at the right height? So it can be kind of like a dynamic trainer for you to show you, are you doing your exercise correctly or not? And again, this like technology works the same way as these 2D cards. There's lenses printed all over the object, and you can see the little lenses like here. And then there are color patterns underneath those lenses that then show up whenever you hold it at the correct angle. Here's another example. This one's my favorite. This is a lamp for your nightstand. if you lay in bed, it shows you good night. But if you actually sit up in bed and you look from a higher angle, it will show you good day. So it's kind of like a really cute example of like a reprogrammable product that is adjustable based on your viewpoint. And obviously, like the resolution right now is like super, super low because, 3D printing technology, it's getting better, but it's not yet as great as, digital display technology. And here's a last example, which I'm also a big fan of. This was an idea from my PhD student as well. Let me show you this one more time. So this is a shoe that when you look down on the shoe, you see, it says cheer up. But anybody else who looks from the side will not see this message. They will just see like a normal gray shoe from the side. So it's kind of like a nice way to have like a personalized message for you to get through the day, but everybody else thinks you're looking like super professional and nobody sees the color pattern in the private message. Okay, and I want to show you one more for the reprogrammable appearances, again, based on a different optical technique. This is based on polarizers. Let me play you the video. So again, this is fully passive, right? There's no electronics inside, no display technology, as you would know it normally. This is solely based on materials and optics. This is a little hard to see here, but it's also changing the color. It's basically as it rotates, the clock takes on different visual appearances. And then this is a COVID visualization. So depending on how you rotate the appearance, you see different data. And then this is a learning tool. If one person looks through the polarizer here, sees one view, and this is the student view, they don't see the solution. So you can look through and the teacher sees something else than the student. So again, I just want to give you like a tiny little bit of detail of how this works. If you're interested in more about these papers, we always have like a 10-page PDF that explains all the technical detail on my lab's website. So how does this work? It's really simple. Again, you can try it yourself if you want. So this uses a birefringent material. Again, it sounds super complicated, but in the end, it's just cellophane that you may use from wrapping your food. And then you need some polarizers. And again, I'm not sure what you had in physics, if that was already a topic or not, but you can buy them on Amazon. They come in sheet form, for instance. Maybe you know them from like doing photos with your camera or from your sunglasses. Maybe if you have sunglasses and you look at the display and you rotate your head, maybe you have realized the colors change sometime. So this is when your sunglasses are polarized. So again, if you just buy some food wrap and you buy these polarizers, you're ready to go with your color changing technology. And I will show you a bit how this works. Again, I understand if that's beyond the 8 a.m. processing capability, but I hope I can help you a little bit to understand this. So how does the color appear? So on the left side, you see the very basic stack that we use. So we have a polarizer sheet on the bottom. We have a polarizer sheet on the top here. It's called the analyzer, but it's the same material. So polarizer on the top, polarizer on the bottom. And you put your cellophane plastic wrap in the middle. So if they are all aligned, they have a specific direction. And if they are all aligned in the correct direction, the color will be transparent. Now, if you rotate, for instance, the cellophane layer around, as you rotate it, you will see the color will start appearing because of the polarizing effect. And the color will increase in saturation. You can see this in the middle here, the little icon. Will increase in saturation until you hit 45 degrees to the polarizer. And then it will start to become more transparent again until you hit 90 degrees towards the polarizer. And then this pattern continues as you go around. So it's always like more color, transparent again, color, transparent again, color, transparent, color, transparent. So if you're more interested in how the polarizing works, maybe ask your physics teacher. I'm sure they can tell you more about this as well. So you may also be wondering, how can we make multiple colors? So it's really just stacking more cellophane. So if you have one cellophane sheet, you get, let's say, dark blue. If you have two, you get orange. If you have three, you get a green. So literally, if you want to have different colors, you just stack more sheets on top of each other in a specific array. And then the last thing I want to show you for this project is how can we make a transition from one color to the next color. So let's say we had these two different appearances here. Let's say we have the image on the left and we want to go to the image on the right. Again, you can see like in little images drawn out here the stack. So we have again the polarizer on the top, polarizer on the bottom. And now we have two different cellophane arrangements, like each making one image. And then if everything is aligned, that particular image will be transparent. So you can see this in the left column here, the one image that is the same direction as the polarizers is transparent, you don't see it. But the image that is 45 degrees, that one you see, right? And if you go to the right side, it's actually the opposite, right? So the image you saw on the left is now further rotated to 90 degrees. And as I said, 0 is the same as 90, so that one is transparent. But the other one is now at 45 degrees, and that's why you see it. So it's really just a matter of making sure these things are rotated with respect to each other at the right angles to create these different appearances. And I just wanted to show this segment of the video one more time. So this is basically how we go from, let's say, this color to this other color. You see how we are literally just rotating 45 degrees with this little knob here, right? And that's also how this visualization here worked. You see how we rotate the knob by another 45 degrees, and that's changing, fading out one of the appearances and fading out another appearance. Okie doke, so I showed you a bunch of different things for appearances. Obviously, appearance is not everything, right? There's also sensing and interaction capabilities, and I want to show you a few more projects on this as well. So in my team, we love airbrushing and graffiti. We just think it's the coolest thing in the world, and that's why we do a lot of projects with graffiti type technology. So in this project here, we use an airbrush and we load in copper ink. And if you load in copper ink, you can actually spray wires and circuits onto walls, for instance, or on any object. So what we sprayed on here is basically two sliders. So you can see there's like different segments, and each segment has a wire. So if you put all of these segments together and you move your hand over it, like each wire will be like touch, 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 touch. So you know like where the hand is on the overall slider geometry. Since it's airbrushing, we can obviously also put on some color, right? So, the copper didn't look so pretty, so we put on a bit of more like a decorative design. And now we have a functional user interface where we sprayed this like on and off button here with a little display that turns the lamp on and off. And then the sliders hidden underneath this decorative design here can set how bright the light should be and can also set, for instance, the color. And again, it's super doable, right? You just need an airbrush can, you need these materials, you can buy them online, and you can spray your own like user interfaces. You connect like an Arduino or whatever microcontroller you may have used if you do some making activities, and you can go for it and build this yourself. So I just want to show a bit more on these materials. We specifically buy them from a company called Lumilor, and you can, just buy them as a copper, for instance, and you can make touch sensors, sliders, you can make wires, and you can also make like microcontroller connectors. And they also have another material, which is really cool. It's also conductive, but it's transparent. And because it's transparent, you can actually put it on objects and nobody sees it. So I want to show you one example where you can actually not really see that the object was augmented. So we used the couch in my research lab, and we were like, okay, let's spray on like some touch sensors and some backrest sensors so we can actually measure if a person is sitting on the couch and interacting with the couch. And again, it's very simple, right? We just bought this airbrush can here and we loaded the material and we spray it on. You can see it is conductive here. Oops. And then we can build like really fun application examples where, for instance, here we can, oops, let me just play the video one more time, where we can detect if somebody's sitting down. Here we load a photo album automatically once the person sits down, and then they can swipe using the armrest back and forth. Yeah, just like you would use your phone, but you can interact directly on the object. And again, the couch still looks normal, like nobody would get upset if you spray something on the couch because it's not visible. So it's a really great opportunity to add interactivity to objects. Okay, So in my lab, we also always build some sort of like 3D editing software to support the maker or the user. So here you can just see like our software for laying out all the elements. And then we have a projection system that projects these elements onto the couch so you actually know where exactly you have to spray and put your material. So this is one more thing where we kind of like vandalized our research lab. Please don't do it in your school, it's not recommended. But we sprayed like a user interface on the columns of our research lab. So you can see there are these like music notes here, and each music note has a wire, and these wires then connect to a microcontroller. So actually when you touch the wire, when you touch the music note, you have like an interactive music playing application because the touch signal is then forwarded to Spotify, and you can actually go to the next song or go to the previous song using this interface in our lab. Okay, cool. I want to show you one more example for this like integrating sensing with objects. Here we were wondering, like, you know, if you buy anything that has interactivity these days, like you buy your phone or even your mouse, right? Everything has like a ton of electronic components inside, and those need to be assembled in a factory, and all the parts need to be ordered. And we were wondering, can we just 3D print something in one go, in one object, without all of this assembly stuff? So we developed a technique to print like very simple objects, but just to give you an idea where we can actually do some sort of sensing. So here, this is a Pac-Man game, and this is a little joystick. So you can see how as the joystick moves, the Pac-Man, for instance, moves to the right direction. So the way we do this is oh, I actually have a pointer. Okay, that's cool. We 3D print conductive walls. So we 3D print with two different materials, with a normal material on the outside and then a conductive material on the inside. And then we measure the relationship between these two conductive walls here, for instance. So let's say if you move the joystick to the right, the distance would increase between these two conductive walls. And we can measure this as a change in something called capacitance. And we can detect this with our microcontroller and then, you know, determine where the joystick is moving. The same if you move these walls closer together, the capacitance increases. And again, we can measure how large is the capacitance so we exactly know where the joystick is positioned. So you can see this here one more time. Again, these copper-looking walls are conductive. And as they get closer together, you can see how we can actually measure this with our microcontroller and then replicate on the computer screen. So this is basically how you saw like the joystick works. We just check out how close are these walls by changes in capacitance that you can measure. So again, it's very simple technology. So really, you know, we don't do magic. We don't need a lot of money to do our research projects. It just needs a 3D printer that can print two different materials. You can buy those materials online. One that we use is a flexible material called Ninja Flex. And then the other one is a conductive material that you can also buy. It's called Electrify. You just load them in the printer, you print it out. And then we have a little processing board and a software that computes those signals to make the interactivity happen. So you have a few more examples. This is a kind of like a fun music controller. You can like hold it in your hand and squeeze it. And again, as you squeeze it, the walls of these conductive cells change their distance, and we can measure these distance changes and then send it to a software like, you know, Guitar Hero or Guitar Band or like Max MSP, you know, anything that you use for like music controlling. This is the same sensor as you have in your phone, like an accelerometer that measures, you know, acceleration. And again, we can measure this because we measure the distance between the conductive walls. So as the middle element swings, right, we can check how large is the distance between the top two walls and the bottom two walls, and we can actually make these different sensors. Same principle for the rotation sensor here. Again, we just check like how close are these conductive elements to each other, and we can measure this as well. Okay, so this was about integrating sensing. So sensing is cool, but you know, actuation is even cooler. So we were wondering, is there like a way to also make like fully functional objects that are actually actuated, and you can just download them and you can make them on a regular fabrication device? So I will show you like this example really quickly here, how we actually make a drone that flies right out of the fabrication device. So I'm not sure how much you know about like 3D printers and laser cutters, we will use a laser cutter, and a laser cutter is basically a machine. It has a laser integrated, and it can cut out 2D paths from material sheets like acrylic or wood, for instance. And we augmented this laser cutter with a custom add-on that can make all sorts of functional components by extruding silver and then also picking and placing components. So I will just show you the video here. So this is the inside of the laser cutter. You see it's currently cutting out the shape of the object, of the drone here. And then there's a little silver extrusion head. It's a little bit hard to see, but I hope you can see how it's making the conductive traces to add the functionality. So now we are going to pick and place some components we positioned on the right side. These will be our rotors for flying, and then also our microcontroller for doing the computation, so the drone knows what to do and where to go. And then the last step we will do, oops. I hope it's not too laggy on your side. So let me play the segment again. So we are putting the last rotor blade down. And then the last thing we will do is we will cure the silver with the laser again. So you see the laser is going around one more time. It's making the silver conductive now by heat curing it. And once it's done, like the last path is cured, you will see there's a little light that will come on the quadcopter. And it will simply like fly out of the bed. So the rotors come on and then whoop, there it goes. So the idea here really is, maybe in the future we have actually like machines that can deploy devices themselves, right? Maybe you're not even saying, I want to download this. Maybe there's just some, AI in your home that's like, oh, I need a new robot or I need a new helper, and the fabrication device is just going to make it for you. And then the made object can just like go ahead and maybe go and clean up your room or do something else in the environment. I think that would be an interesting future to think about. Okay, I want to show the system one more time. We built this like really big assembly here for the machine, but the functionality is very simple, as I showed you. It's just like a silver extrusion that we added and a pick and place machine. This is the mechanical drawing here that my student made. Okay, cool. And then this is the last segment I will share with you guys. Again, I'm not sure like what exactly you know in terms of like making, but I thought maybe some of you have done some breadboarding or maybe used the Arduino or something like this. If not, don't worry, but I thought I include something on this as well. So if you have ever done any sort of like electronic prototyping to build something cool for yourself, like something that my students love to build is like, let's say, a smartwatch for themselves where you 3D print a bracelet and then you put like a microcontroller on and you can add like all sorts of functions. You may have realized that prototyping with breadboards is cool, it's very helpful, but it also makes everything like really clunky. So if you really just wanted to have like a nice bracelet here, right, you will have like this huge electronics assembly on your arm, which doesn't look so good. So we had like two ideas. We were thinking, can we make this better and more integrated? So I will show you two things here. One project we did is called Curveboard. So the idea was, can we integrate this like clunky breadboard directly with the object you are making? So here you see the breadboard's actually integrated into the surface of the object directly. So let's say you're prototyping this like fancy headphones here and you want to add your own display and your own button functionality. With our curve boards, you can see how all the breadboard rows and columns are directly integrated with the headphones. So you can like plug it right in and you can prototype right on the headset here. We have an editor for this because we love making editors. So we have a 3D editor plugin that converts any 3D model you want into a breadboard. So here, this is like this bracelet that we are making, and you see all the pinholes are already on the 3D model. And like once you have all the pinholes there, you can make your own breadboard layout. You can say, I want to have the rows like this or the columns like this. And once you're done like laying out your, making your layout, we compute all the holes and the channels for your custom breadboard. And then all you do is you 3D print it out on your 3D printer. And once you have it 3D printed, because the conductive printing is not yet like really good, we use conductive silicone and we just like fill all the holes. So conductive silicone is very easy to make. You just take normal silicone and you put in some conductive particles and you mix everything together, and that's basically all we do. So again, everything's very DIY and doable if you're interested in replicating this. And then once you have your curved board, you can use it as a normal breadboard. So you can like plug your components, you can plug your wires, put everything together, and once you're done, everything is still functional and you can just use it like a normal breadboard. I will just like forward this a bit. So you see everything's connected. We plug in the microcontroller here, and then the display just comes on like you would expect it from a normal breadboard. So we thought, okay, this was kind of cool, but on the flip side, this was good for form function integration, but then it also takes a lot of time for 3D printing. So if you really just want to make a quick prototype, maybe you don't want to 3D print everything first before you do your breadboarding. So we were wondering, is there another way? And I want to show you here this like second project. This is also like just finished, and I've not shown it to anyone except you guys. This is called Flexboard. So we are basically just taking a normal breadboard and making it flexible. And you can see this here. You can literally like bend our Flexboard and just put it on. And let's say here we are like prototyping this kettlebell, and we notice, oh, it's not quite right. We can actually also like cut our breadboard into pieces. And then, we have like our breadboard is kind of like a roll that you can just cut into like different sections, and you can wrap it around the objects, and you can kind of like breadboard as you go along. And again, this is not magic. It's totally, if you have a maker shop, you can totally do this yourself. I will show you how we did it. We 3D print this kind of flexible hinge pattern that makes it bendable. And then we open up a traditional breadboard and we just rip out all the metal stripes. And then we simply reinsert all these metal stripes into our flexible structure. And that's really all you need to make like a flexible breadboard. Yeah, okay, great. So, yeah, you can see this here one more time. This is for making an interactive glove. Again, if you have ever prototyped something that's deformable, like normal breadboards are just annoying because they're super rigid. But with our Flexboard, you can make like different rows, connect everything, bend it, and then attach it to your glove and use it for prototyping. So here in this case, we also use like a sewing just to attach the breadboard to the glove. So we sew it on. That's what you see here in like 1000x. And then, you can just do your normal prototyping of the interactive glove. And yeah, if you're smiling over all the typos we have in the video, this was done by one of my Korean students, so his English is not the best, but I will do an iteration with him once we are done. Okay, great. So yeah, I just want to show you these for like, better function and form integration, which I think is also a really relevant topic. Okay, so I don't want to talk any longer. I just want to zoom out and show you the overview one more time. So for me, it's like really important to think about, in digital, we have all of these cool capabilities already, but in physical, we are still like super, super limited, right? And I showed you a little bit on the appearance front, right? It's not that magically you can like recolor your objects today, right? In digital, super easy. You apply a new photo filter, everything is good. So can we do something like this in the physical world as well? Right, and the same with sensing, right? In digital, like wherever you click on your screen, right, your computer always knows what you're doing and how you're interacting. In the physical world, everything is passive. Your couch doesn't know you're sitting on it. Wherever you're walking, nothing is being sensed. So can we bring this sensing to our physical environments as well? And then, not just sensing, but also like actuation, right? Can we make things that can just like, walk out of the fabrication device, fly off and do their thing in our physical environments and change things like our digital programs would do for us. And then finally, I also wanted to show you these projects just for like making prototyping easier and more integrated with, whatever you're building as a shape. So I want to take a moment. I have a big research team. So all of my PhD students, master students, we have lots of undergraduate researchers who help us. So big thank you to them. They build all of these different projects. And then I also want to thank all of our sponsors. Research is unfortunately an expensive endeavor, not because of the materials, but mostly because of the people who work on it. So big thank you to those people as well. And then with this, I want to wrap it up. I hope it was interesting, and I'm happy to take any questions as well.
Okay, thank you so much, Professor Stefanie Mueller. I hope everybody is able to listen to me. Otherwise, just please give me a sign. There's been some applause here. Thank you, Micha. Applause by all the others. So thanks a lot for your very, very interesting talk. I'm Thomas Spahn, head of high school here at GISSV. For the guests from New York who don't know me yet, hi.